Hello and welcome to today's lecture on horn antennas. But horn antennas are known as standard gain horn antenna. So, that is one of the major application of horn antenna, and another application where horn antennas are used extensively and they are used as a feed for large reflector antenna. So, these horn antennas are placed at the focal of the parabolic reflector, and that is how the excitation takes place. But just to tell you about the standard gain horn antenna, so I just want to tell something practical experience which we gained. So, I have been teaching a horn antenna since 1992 at IIT Bombay, but it was actually in around 2005 when I started my own company Wilcom Technologies Private Limited, which was incubated through IIT Bombay, and we had supplied some antennas to the industry. And then they asked me, have you calibrated the gain of the antenna? I said, yes, we have done the testing, we have done the simulation, and these are the results. But they said, no, have you compared with the standard gain horn antenna? And we said, no, we have not done that. He said, no, till then we are not satisfied. So, then I went through the internet and I saw, so typically any standard gain horn antenna, the cost would be about at least 1 lakh rupee, and I did not want to spend that kind of a money, and I felt that since I have been teaching horn antenna for more than a decade, why not I should design myself. And then even though I was teaching this course for so many years, when it came to the final fabrication, then I realized lot of things are not available, and one of the major thing which I found it was not available was how to properly feed the horn antenna. And then we started doing lot of work, we did the design and then we fabricated ourselves and so on. Today let us start with the horn antenna, and we will tell you what is there in the textbook and what needs to be modified, what are the things given in the textbook, and then we will also tell you something which is not given in the textbook. So, let us start with the horn antennas. So, today we will start about horn antennas. So, in the horn antennas, these are the commonly used horn antenna. So, what are these here? This is actually a E plane sectoral horn antenna, this is a H plane sectoral horn antenna, and this is pyramidal horn antenna. So, what it is actually you need to start with the, let us say this is a rectangular waveguide, and in the rectangular waveguide we operate this rectangular waveguide in the fundamental TE10 mode. And what TE10 mode implies that there is a 1 half wavelength variation along this direction. So, that means along this direction there will be a lambda by 2 variation and 0 variation along this particular direction here. So, one can actually see that since it is a metallic body, so the voltage will be 0 here and voltage will be 0 here, and for lambda by 2 to happen, so this voltage which is 0 here goes to the maxima and comes to back to 0 here. So, this is the electric field variation or voltage variation along this particular axis, and you can see that these fields are uniform. So, there is a no variation along this particular direction. So, this is the E plane. So, if we flare only in this particular direction, it is known as E plane sectoral horn. So, basically the width of the waveguide has been expanded in this particular direction, and orthogonal to E plane will be H plane. So, if we expand this whole thing in H plane direction, this is known as H plane sectoral horn antenna, and if the dimensions are expanded in both the direction, that means in E plane as well as in the H plane, this is what the configuration looks like, and this configuration looks something similar to a pyramid, and hence it is known as pyramidal horn antenna. And this is a conical horn antenna. So, where basically it is a circular waveguide. So, you can see this is a circular waveguide, and then one end of the waveguide is expanded and that becomes a cone. So, this is the reason why this is known as conical horn antenna. But today we will concentrate mainly on the sectoral horn antenna, and then we will go to pyramidal, and then much later we will go to conical horn antenna. So, let us first start with the simple rectangular waveguide, because we need to understand how a rectangular waveguide works. I am sure all of you might have taken electromagnetic waves course where you would have studied rectangular waveguide, but just a quick brush up. So, let us say a rectangular waveguide is defined by its broad wall, and this is known as a narrow wall. So, this broad wall dimension is given by A, and this one here is height is B. So, for fundamental T10 mode, as I mentioned, so 1 corresponds to that E field varies from here to here, which is a 1/2 wavelength. So, that means this is 0 field here, and this one goes to maxima and then goes to 0. So, that is half wavelength variation. So, 1 implies that, and 0 means uniform field distribution. So, that is what it is. So, now for this particular case, E field varies sinusoidally along A, and it is uniform along B, which is what it is, and H field will be perpendicular to this E field here. Now, waveguides are defined by its different band. So, this is a X band waveguide, and there is a symbol for that, this is known as a WR90. There is a very specific significance of these numbers actually. What these numbers really imply, that A dimension is equal to 0.90 inches. Okay. So, if instead of 90, suppose if this is say 230, then that will be 2.3 inches will be A. Suppose if this is WR 2300, so if it is 2300, it will be implying that A will be equal to 23 inches, and this waveguide is designated to operate in the frequency range of 8.4 to 12.4 gigahertz. So, let us see what is the reason why it works in this particular frequency region. So, first of all, now this is the dimension which governs the value of A. So, A is equal to 0.9 inches and B is given as 0.4 inches. I just want to mention here that majority of the other waveguides, they actually have B approximately half of A. So, here this is 0.9, half would have been 0.45, but which is actually 0.4 over here. Now, for this waveguide, we define cutoff wavelength, and cutoff wavelength is given by a very simple formula, which is equal to 2 times A, and 2 multiplied by A is 0.9 inches, convert that into centimeter by multiplying by a factor of 2.54. So, cutoff wavelength is given by this number here, and then we can find out from here what is the cutoff frequency. So, cutoff frequency is given by C divided by lambda, and here C is 3 into 10 to the power 10 centimeter per second, because this dimension is in centimeter. If it was meter, then it would have been 10 to the power 8 meter per second. Then we have to convert this into meter. So, anyway, if we simplify this, this comes out to be 6.56 gigahertz. So, this is the cutoff frequency of this waveguide. So, in general, I want to mention that waveguide is considered as a high pass filter. So, that means below this frequency it will be attenuated, and the propagation will only take place above this frequency. So, now comes the next question, if the cutoff frequency is 6.56 gigahertz, then why this waveguide is defined from 8.4 to 12.4, and why not from 6.6 to 12.4 or other number? Okay, if a waveguide is known as a high pass filter, then a high pass filter has a characteristic that any frequency higher than that it should pass. So, why again this particular limit? In fact, if you look at this limit, it looks like it is a band pass filter. Well, that is not a correct thing. Let me go step by step. So, rectangular waveguide has a cutoff frequency which is equal to 6.56 gigahertz, whereas if you actually see, it is defined that X band waveguide works from 8.4 to 12.4. So, why there is a discrepancy between this number and this number? Now, as I mentioned, a rectangular waveguide is nothing but a high pass filter. So, below this frequency there is a attenuation, so it does not really propagate. But however, just if you think about at 6.6 gigahertz, attenuation is still very high. In fact, I would like to show that if we take attenuation in the vertical axis and then if we take frequency, so suppose we have attenuation in this vertical axis and frequency is going in this way, and let us assume this is the cutoff frequency. So attenuation is very high at cutoff frequency, and this attenuation slowly starts decreasing and then it remains nearly flat. So from here to here, roughly about 1.3 times Fc, which is the cutoff frequency, we have a relatively very small attenuation. So that is why from the frequency region from Fc up to about roughly 1.3 times Fc, it is still, attenuation is still very high, and hence it is not very useful thing. So when you are designing a horn antenna, you must ensure that you are working in a proper region where attenuation in the waveguide itself is relatively small. So let us continue from here further. So this is 6.56, and if you see this operating frequency is 8.4. If you take the ratio of this to this, that is actually equal to about 1.28, which is close to 1.3. Then comes the next part, why there is a limit on the higher frequency. The limit to the higher frequency actually comes because as the frequency increases, that fundamental mode 1-0 mode may actually become a 2-0 mode, or the orthogonal mode may get excited. So majority of the time horn antennas are operated in the fundamental TE10 mode. However, there are some special cases where we use different modes, and when we go to that topic later on, I will tell you where there is a difference, but right now we will focus upon that horn antenna generally will work in the fundamental TE10 mode, and for this particular waveguide, this is the operating frequency range. And if you really see, this is fairly large frequency range. So if you take center frequency of around 10.4, you can see that the bandwidth is close to about 40% or so. And of course, one can choose different thing also. So instead of WR90, suppose you take WR230 or WR340, then correspondingly this range will be different. So we will have to use that particular waveguide wherever we want to use the antenna. So now let us just look at the sectoral horn antenna. So this particular thing here shows E plane sectoral horn antenna. We know that this is A dimension, this is B dimension, and this is the field variation along A, and now this is the E plane and it is being flared in the E plane over here. So since it is being flared up here, this is why it is known as E plane sectoral horn antenna. Now let us just look at the axis also. So this side here is x axis, this one here is y axis, and this is z axis. Now when the wave is launched from here, it is going to propagate in this particular direction, and if the wave propagation is in this direction, then E and H field will be perpendicular to that. So in this case, E is in this direction, H is in this particular direction. So now one can see that E only has a component which is in the y direction. So we have a EY over here, and this EY, E1 is just the constant, and this is the cosine variation along this particular axis, and one can quickly check it. So when x dash is equal to 0, x dash equal to 0 is at the origin. So if x dash is 0, cos 0 will be 1, so that will have a maximum value. If we go to the edge here, at the edge x dash is equal to a by 2, half of this waveguide dimension. So if this is a by 2, that will become cos pi by 2, and cos pi by 2 is equal to 0. So that is why it goes from maxima to 0. So that is the amplitude component. Now this amplitude component, which is at the waveguide, that is being expanded to the aperture of the horn antenna. Now at this particular thing, there will be a phase distribution also. So phase distribution, what is actually happening? So from here the wave is getting launched from here. So phase along the aperture will not be constant, and that is the term here, and this term can be better understood by the next slide. So, this is the side view of the sectoral horn. So, from the side if we see, we will see the dimension b, and then this is expanded in this particular plane here. The total dimension will be b1 and this is b1 by 2, and then we want to define the face center of the horn antenna. The face center of the horn antenna actually is not physically visible as such, one has to imagine and extend the dimension. So, this is what dimension b which has been flared to b1, and if we extend this b1 over here, that will meet at this particular point which is the central point, and if we extend this here, so wherever this part is extended, that becomes the face center of the horn antenna. So, from here to this particular point, we are defining the dimension as rho 1, and this is z axis as before. So, now if you look from this point to this here, if this is rho 1 distance, then we can see that if this was something like this here, so all this dimension will be also equal to rho 1. But if we look at the aperture of the horn antenna, then what we see, the distance will be from here up to this point here, or at the edges the total distance from here to here will be rho times e. So, now the phase error which will come into here, so this is the phase error. So, first let us find out what is this particular distance. So, this distance will be equivalent to total this distance, okay, minus rho 1. Okay. Now, this distance here will be nothing but rho 1 square plus y dash square and square root of that. So, if you see here, it is slightly written in different form. If we take rho 1 inside, this will be rho 1 square, and that will cancel this. So, it will be rho 1 square plus y dash square, and that is what it is, rho 1 square plus y dash square will be this total distance, and from here we subtract minus rho 1. So, now this is the distance delta from here to here, and that distance now can be simplified, this expression. If we expand this here, now please notice I have used the term here approximately. Why approximately? Because higher order terms have been neglected here. So, if you just look at the first term here, so first term will be 1 plus half of this value. So, this is the 1 plus half. So, you can see these two terms will get cancelled, and that half will come here, and half y dash square divided by rho 1, part of 1 rho 1 will get cancelled. So, this is delta y. Now, that is the distance. So, the phase error in terms of degree will be given by the term which is k. So, the k times this particular value here. So, that will be the phase distribution, and one can actually see that. So, when y dash is close to 0, which is at the center point, if we look at, so there will be no phase, that will be the reference phase. And as we go above here, go to the extreme point here, so y dash will become half of b. So, that will give us the maximum phase error. So, if this is considered as a reference phase, maximum phase error will come at the edges. So, one can actually see here. So, phase error you can say starting from here as a reference, and this phase error will keep on increasing like this here. So, here sometimes students do ask a question, what if we, instead of taking a horn antenna like this, why not we take a horn antenna something like this here? So, then there will be no phase error. Yes, at the periphery of the horn there will not be a phase error, but when we talk about the wave which is coming here, and then we talk about a plane wave here, and if you are talking about a plane wave over here, that is what will be parallel to this here. So, phase error will come into picture. So, by making a horn antenna of this shape, it is not going to make that phase error will become equal to 0. However, there are alternate techniques to balance out this phase error, and that is actually many a times one actually uses a lens antenna over here. So, something like this here, if we use the lens antenna, so a lens antenna will have a very small width at this particular point, and over here width will be larger, and if the wave which is propagating through the dielectric media will actually experience more phase delay compared to end over here. So, that is how the phase compensation can be done. So, it is a very, very common practice to employ. One can actually just use one side of lens also like this here, or one can use a lens like this also. So, both the things are possible, and basically these are done to adjust for the phase error. But otherwise, if we do not have that option, then what we do, we put a restriction that this phase error should be relatively small. So, let us just see some examples, and first we will start with the directivity curve. So, I just want to mention here these directivity curves have been reported in the literature. So, these things are there. So, let us utilize the knowledge which has been given by so many researchers in the past. So, what I want to show over here is that this is the normalized directivity, because one of the dimension of the waveguide is constant, which is not being changed. So, A is constant, so that is what it is coming over here, this is lambda. So, it is basically normalized with respect to that. What do we see over here? This is actually the horn aperture dimension, which is B1. So, basically B1 is getting increase in this particular thing. That means we are increasing the aperture dimension. Now, what are these different curves here? These are the different curves for different values of rho 1. So, if rho 1 is 100 lambda, that means the horn antenna is very, very large, and over here you can see rho 1 is about 6 lambda. So, it is relatively shorter. So, that means the length of the horn antenna is relatively short. So, suppose that we have a fixed horn length which is 6 lambda, and then now for this fixed 6 lambda, let us see what is happening if we increase the value of the B1 continuously. So, what happens? You can see that the directivity is increasing, and then the directivity becomes maxima, and then it starts reducing. So, why it is reducing? The reason for that is, let us say now we are increasing the aperture, and okay, so this distance is nothing but equal to the rho 1 plus B1 by 2 whole square, and if B1 is relatively small, phase error will be relatively small. But as we keep on, for the fixed length of rho 1, as we keep on increasing this dimension, so what will happen? Phase error will start increasing, and now let us just see the wave is propagating in z direction, and what we have seen, E field is like this. So, if E field is like this here, but now there is a phase error. So, because of the phase error, it will not be aligned in this, it will be now aligned like this, then it will get aligned like this, then it will, if the phase error becomes 90 degree, it is actually going in this direction. That means contribution of this will be negligible or not there. But if you increase the phase further, now what is happening? This plane vector will be like this. So, this was starting was in this direction, and this is in the opposite direction. So, what will happen? Even though you are increasing the aperture, this field and this field here, they will start cancelling each other, and hence directivity will start decreasing. So, there is an optimum value up to what level you can increase the value of B1, till then you can get a directivity which is increasing. After that, directivity will start decreasing. So, let us just look at this curve again. So, one can actually see that as we keep on increasing the value of B1, we can see that the directivity is increasing, and then it starts decreasing. The same thing happens here. Suppose if I take this particular length, you can see directivity is increasing up to this here, and then it starts decreasing. If we take this one here, directivity starts decreasing after this value. So, from here we can actually just draw the line from here. So, if you think about this is 6 lambda, if you draw the line somewhere over here, you can see this is the value of B1. So, I have written here rho 1 is 6, then B1 is approximately this value. If rho 1 is 10, you can just again draw the line here, and that is this value here. And if you go to 100, one can actually draw the line here, you can actually see that will be somewhere here, which is 14. And if you actually put this thing here, this whole thing can be actually drawn, a line can be drawn through here which will go through the maximum value, and that equation is given by B1 equal to square root 2 lambda rho 1. Now, these are the values which are given, and this is what it suggests, that this is the value which for which we get maximum directivity, which is over here. So, let us see now this corresponds to how much phase error. So, maximum directivity occurs when B1 is equal to this particular expression here, and we also know that maximum phase error occurs when y dash is equal to B1 by 2, that is at the end of the aperture. So, now we can find the value of delta. Delta expression was given over here, and we know that the phase term will have a 2 pi times this here, and where s is given by this term here, we can actually see y dash is equal to B1 by 2. So, that will become B1 square by 4, 2 is already there, and this rho 1 and lambda is coming because of that 2 pi by lambda, which is the k term for phase, it is coming over here. So, now if we substitute this value of B1 over here, so S optimum according to this, we substitute the value, it comes out to be 1 by 4, and if we put S value equal to 1 by 4 over here, this whole thing becomes delta max equal to 90 degree. So, this is what majority of the books tell you, but I do not agree with this particular thing. Phase error is just too high, and I do not recommend that you should go to this particular phase error. In fact, let us go back and look at the directivity curve one more time. So, what we really see here is that this is the point where we get the maximum directivity, but this point also implies 90 degree phase difference. But just think about it, that instead of this phase error, if I had taken up to this point only, then I would have got little lesser directivity, but this is linearly increasing, and we know that directivity, general expression of directivity is nothing but we can say 4 pi area divided by lambda square, and area is nothing but a dimension multiplied by B1. Here a is constant and we are increasing B1, so it should have been linearly increasing, but over here it is not increasing. So, if you just look at this particular point only, we say this is the maximum directivity point, absolutely right, but however, if you look at it theoretically, had this phase error not come into picture, and if we draw the line vertically up, it would have actually gone somewhere here. So, we could have got the directivity this much here if there was a lesser phase error. So, in fact, I never ever recommend that you design the antenna for about 90 degree phase error. In fact, our recommendation is design most of the time only for a phase error of about 45 degree. And I also want to show you now the E plane pattern here. So, this is the E plane sectoral pattern, this is known as a universal pattern, and this universal pattern, if you look into that, this is the E plane curve here, this is the field variation, and this one here basically corresponds to when the phase error is very less, okay, and if the phase error is very less, we can see that there are sharp nulls are there, whereas if the phase error, if you see now for 1 by 8, you can see that some nulls are coming, they are not very sharp, but if we take phase error equal to 90 degree, you can see now this is the variation, and if you see these value, this is about close to minus 10 dB, and you can see this is a much broader region, and this is radiating in the undesired direction, and minus 10 dB is like 10%. So, 10% of the power is getting radiated here, here and everywhere. So, resulting into the lower gain and hence lower efficiency. So, in fact, if one takes this kind of a number here delta mx 90 degree, then efficiency obtained is of the order of 50 to 60%, whereas if we take number something like this here, then the efficiency can be 70 to 80%. So, we would rather like to design an antenna which is more efficient rather than going with this particular phase error. In fact, I also want to mention this entire thing can be also explained in the form of the array theory also. So, I will mention about that in our next lecture, how this E field pattern can be explained using a very simple array theory concept also. So, just to summarize, we started talking about horn antenna and we looked into various types of horn antenna. There can be E plane sectoral horn, H plane sectoral horn, pyramidal horn and conical horn antenna, and much later we will talk about variations of these horn antenna also. So, we looked into the another part, that is the directivity of the horn antenna increases up to a point and after that it starts decreasing. The main reason is that the phase error starts increasing, and because of the phase error the fields start cancelling each other and hence directivity decreases, efficiency decreases. So, we will continue from here in the next lecture. So, till then, bye, have a good time.